Okay, so what we have done in the last lecture, that an SU2 rotation on this signal zeta 1 zeta 2. Okay, so this is actually equivalent, it's equivalent, identical to O3 transformation on x, y, z. So what does that mean? Suppose if you are having, okay, you make a rotation in three-dimensional space by r. Okay, so that's actually equivalent to the same to a rotation in two-dimensional plane. Sorry, in the two-dimensional space, not plane, in two-dimensional Hilbert space. Clear? Got it? Okay. So now, if you remember, so how they are connected, how the elements of the transformations are connected. Okay. So how they are connected? Yesterday we have seen x minus iy is equal to minus zeta square, x plus iy is equal to zeta 2 square, and z is equal to zeta 1 zeta 2. So this we have derived yesterday. So this is how the elements of the transformation are related. Okay, so how these are related? Look, x, y and z, they are the components of a vector r. That column vector, is it? Zeta 1 and zeta 2 are the components of this column vector, is it? Samashivan? You got my point? Okay, so you can calculate. Okay, so we will take in examples. So 1 by 2 zeta 2 square minus zeta 1 square. So y you can get 1 by 2i zeta 1 square plus zeta 2 square, and z it is equal to zeta 1 zeta 2. Okay, got it? You got my point? Okay, so now let's try to figure out the transformation detail. Suppose if I make a transformation, okay, so let me make a transformation in x plane, this in three-dimensional space. Clear? So what will happen? So let's make a transformation. So this r will change to where? R prime. So let's make a rotation. So I'll be having r. Clear? So let me put a vector here. Got it? So what are now the transformed coordinates? So it will be x prime, then I'll be having y prime and z prime. Is that true? Okay. So now how they are related to now the primate coordinates in that two-dimensional space? So they will be related like this way: 1 by 2 zeta 2 prime square minus zeta 1 prime square, 1 by 2i zeta 1 square, okay, prime, plus zeta 2 prime square, and then it will be what? Zeta 1 prime zeta 2 prime. Clear? Now tell me how these zeta 1 and zeta 2 transform under SU2. Okay, yes, under SU2, okay, so we are having the zeta 1 prime is equal to, anybody? A zeta 1, yes, it is something like the zeta 1 prime, zeta 2 prime, that's equal to u zeta 1, zeta 2. So you can write it as like this thing, b zeta 2, and then you are having this zeta 2 prime is equal to minus b star zeta 1 plus a star zeta 2. Clear? Got it? Samajh aa? So now you can substitute this zeta 1 prime and zeta 2 prime in this set of equations. Let's call this as equation 1, or let's call this as equation 2. Call this set of equations as equation 1, and call this set of equations as equation 3. Now let's use 3 in where? 2. So what you will get? You will get x prime, y prime, z prime in terms of what? Zeta 1 and zeta 2. not only zeta 1 and zeta 2, you will get actually in terms of A, B. Samajh? You got my point? Now tell me, what are these x prime, y prime, z prime? These are the coordinates of the vector which transform under SO3. Sorry, O3, not SO3, which transform under O3. Clear? You got my point? And what are these A, B? These are the coefficients in SU2, is it? Or these are the elements of an SU2, U. Clear? This U matrix. You got it? So now let's substitute it here. Now in a moment you will, I think, appreciate this very relation. Okay, so what you will get? So you will get x prime. So shall I put the result directly? Okay, so now what you will do, so once you will substitute this zeta, okay, so wait a sec, look here. So you substitute zeta 1 prime, zeta 2 prime here, is it? What you will get ultimately? In terms of zeta 1 and zeta 2. Then combine them in the form like this thing. Zeta 2 square minus zeta 1 square, what you will write for that? X. Clear? So that means I want to get a relation between x prime and x in terms of the elements of SU2. Clear? Because, and why? Because we have seen this SU2 induces actually a rotation. Clear? So that's why. Okay, so let me write, maybe you, okay, so use 3 in second. Clear? Then equation 1. Samajh aaya? So what you will get x prime as 1 by 2 a square plus a star square minus b square minus b star square x minus I by 2 a square minus a star square plus b square minus b star square y minus a star b star plus ab z. Okay, then you will get y prime as I by 2 a square minus a star square minus b square plus b star square x plus 1 by 2 a square plus a star square plus b square plus b star square y, okay, minus I a b minus a star b star z. Okay, okay, so z prime you will get. Okay, now you can appreciate the result. Okay, z prime is equal to ab star plus, so this is actually a little bit hard to digest at first step, but once you do it at your places, so you will appreciate these results. Okay, at your level it is this kind of, we call it as an isomorphism. It's a little bit difficult to understand at the first reading. So once you will do at your places, you will feel better. Okay, you will learn it in a better fashion. Okay, now what we have done? Okay, so we have written x primes in terms of x, is it? So primary coordinates, so that means we have done actually a rotation, let's say in 3-dimensional space, or in O3 we have made an O3 transformation, but represent that transformation in terms of the SU2. Clear? So because this A, B, A star, B star, they are the entries of a SU2 matrix. Clear? So that means it forms a relation between what? An SU2 and O3. Clear? Okay, so now let's take the specific examples. Clear? Okay. Let's take the first example. Let's take this A is equal to e raised for I alpha and B is equal to 0. Clear? So what is the magnitude here? Let me take alpha by 2. Okay, so what should be the determinant? Now tell me. So now let's write this u first. Okay, so let's write u. What is u? E raised for I alpha by 2, B is equal to 0, 0, what it is? it is A star. It is minus alpha by 2. So that means this represents the element of an SU2. Clear? Is it? So if I define now my Pauli spin matrix sigma z as 1 0 0 minus 1. So this I can write as e raised power I alpha by 2 sigma z. Okay? So now you can expand it in terms of the exponential. 1 plus I alpha by 2 sigma z plus sigma z square. Clear? So you will see it will be of this fashion. समझ आवा? Everybody followed it? So that means an SU2 transformation is induced by this sigma z. What is the parameter here? Is alpha a parameter? Alpha you can think it is an angle. In two-dimensional space it is an angle. Okay, so now let's look at this very thing, a corresponding three-dimensional rotation. Okay, or O3 transformation. Now let's look. So what will be x prime? Now tell me what is x prime. So B is 0, B star is 0. Clear? What you are having? A square plus A star square. So since I am taking A is equal to e raised for alpha by 2, A square will be simply e raised for I alpha. Clear? So you will be having simply it here 1 by 2 e raised for I alpha plus e raised for minus I alpha. Clear? So this will be 0 x. Then you are having plus this. Okay, sorry, minus I by 2. So what you are having? E raised for I alpha minus e raised for minus I alpha y. And z is equal to 0. The last term is 0. Clear? So now tell me what this is equal to. It will be x prime. Okay, so let me write now y prime. It is I by 2 a square e raised for I alpha a star square. So it is e raised for minus I alpha x. Then it is plus 1 by 2. It is e raised for I alpha plus e raised for minus I alpha y. And z prime is equal to. Okay, so this term is 0. This is 0. What is mod of a square minus mod of b square? It's 1. What is mod of a square? 1. Mod of b square? 0. So it is simply z. Now tell me what this transformation yields me. X prime is equal to cosine of alpha x, then minus, is it okay, plus sine of alpha y, and y prime is equal to minus sine of alpha x plus cosine of alpha y. Then z prime is equal to, so what this is? Just tell me. It's a rotation. It's a rotation in about z axis. It is a rotation about z axis. That means it is rotation in xy plane. Clear? So that, okay, now tell me how I write this rotation. Now we have done the rotation group. So how we write this rotation about z axis? So let me write it is a rotation about z axis through an angle alpha. How we write it? E raised for I alpha jz. Clear? And jz is the generator of the rotation. Is it true? Is this how we write it? And jz we know what is the generator, and you will get the same thing. समझ आवा? So now look here. Is this okay? So if you look at this thing, this is actually a rotation about z axis again. So in a two-dimensional plane, it is rotation about sigma z. You can think of there is a z axis. Clear? So what does that mean? It's a rotation in xy plane. समझ है मन? समझ क्या समझ? So that means a rotation induced by sigma z here is same as the rotation induced by jz. समझ क्या समझ? So that means these are two equivalent transformations. समझ क्या समझ? So here I can write therefore, okay. Okay, now tell me, what is the generator here of this very transformation? Sigma z. Clear? And sigma z, this is the generator. Okay? What is the parameter? Alpha. Clear? So in other words, I can write this. Okay? Let me write u of alpha. This is actually equivalent to this rz of alpha. Okay? I should write it in this way. So it is equal to e raised for I alpha sigma z by 2. So this is equivalent to the rotation in 3 dimensions, e raised for I alpha g z. So Mashima, now remember there is a factor of 1 by 2 here, and there is no factor of 1 by 2, and this plays very important role, this half. So Mashima, clear? Okay, we'll see in a moment. Okay, now let's check it. Let's check that here. Now, if I make alpha to 2 pi, okay, if I am in 3 dimensions, I am making a rotation through a 2 pi, is it? While I will get. So let's say you started with some point alpha, and when you do alpha plus 2 pi, so you will reach to the same point, is it? So you can check here. So you are having e raised for I alpha plus 2 pi, okay, jz. So that's equal to e raised for I, okay. Is it? So it is 2 pi. So it will be simply e raised for I alpha jz. Clear? So after 2 pi rotation, you will get the same thing. But here, if you see what you will get, you will get e raised for I pi. So what you will get? Alpha plus 2 pi, because there is 2 in the denominator. So 2 pi divided by 2, you will be e raised for I pi. So how much is that? So it is minus 1. Is it? So that means you don't get back to the same point. So in the 2-dimensional space, you don't get how many rotations you require? Actually a rotation of 4 pi. Samajh? A 2 pi, then a 2 pi. Clear? So it's a peculiarity of this 2-dimensional space. Okay, this signal space, you require actually 2 rotations, 4 pi rotation to come back to the same point. Okay, so this is a peculiarity of spin half particles. Samajh? So that's why this 2 plays very important role. You should remember that now if you are having, you will be having actually 2 rotations. 2 pi rotations are actually same as what? 1 2 pi rotation. Clear? Or identical. I should say isomorphic. I should not say same, they are isomorphic in each other. In other words, there is a 2 to 1 mapping. So you are having one set of elements, okay, okay, for which 2 elements map to the 1 element of the other set. So it is 2 to 1 mapping. Clear? Got it? Okay. So now let me take another example. So if you take now B is equal to, that is one and the same thing. E raised for I alpha, and A you take 0, you will get actually sigma Z. Okay? Okay, you can take. Now let me take, okay, I think, so let's take that example. Okay, let me take this example. Okay, so A is equal to cosine of beta by 2 and B is equal to sine of beta by 2. So what is mod of A square plus mod of B square? That's 1. So that means determinant is equal to 1. Now let's write the U element. So how is that? What is it? So it is cosine of beta by 2. What it is? Sine of beta by 2. What this is? Minus sine of beta by 2. What this is? Cosine of beta by 2. Can you tell me what is the matrix corresponding to this thing? It contains both diagonal as well as off diagonal terms. So if you, so now let's take the sigma x. So it will be something like e raised for I, let's say beta is an angle sigma x by 2. Okay, and sigma x is what? It is the Pauli spin matrix. Now let's check. So let's take the first term, that is identity, 1 plus beta sigma x, is it? What is sigma x square next term? So it is identity plus I beta sigma x by 2, then minus beta square by 4 2 factorial sigma x square and so on. Clear? So what this is? Identity, sigma x is what? Off diagonal terms. And what you are having? Sigma x square, again identity. So on identity you will be having 1, then minus beta by 2 square. Okay, 1, is it? So it will give you the cos of beta by 2. Off diagonal terms we will give what? It is beta by 2, is it? I times beta by 2 and so on. Clear? So it will give you sine. So Can you check it? So it will simply, this object will yield you this thing. Clear? समझ आओ? Not sigma x, it should be sigma y. Sigma y, because it contains I, is it? So it should be sigma y. Now let's calculate. Okay, sorry, sigma y square. So what this is sigma y? It is containing minus I, is it? So you will be having I into minus I, that's plus. So you will be having beta by 2. This cubic term will be having sigma y again, is it? So you will be having beta cube by 3 factorial. What is that? X minus x cube by 3 factorial and so on. What that gives you? Sine. So you will get sine factor here. Okay? And the diagonal terms will give what? 1 plus 1 minus beta square. Okay. Beta square by 2 factorial and so on. What that will give you? Cos. Okay? So you will get a cosine term here. So that means this, if I choose the parameters in this way, you will get actually a rotation in zx plane. Clear? So now let's calculate the corresponding what? Tell me. In the O3. Clear? So you need to put what? For A and B. Can you do it? Just you substitute for A star, B and B star. Clear? And you will get the same thing. So what I will ultimately get, you will get actually Ry through an angle beta. Can you tell me? So it is e raised power I beta jy. So what is that equal to? Anybody? Since it is in which plane? It is in which plane? It's in xz plane. So that is, it is about y-axis. Why you keep as such? 1. So it is cosine of beta. Okay. 0 sine of beta. 0 0 minus sine of beta cosine of beta. Clear? समझ आया? You followed it? Okay, so that means these two are equivalent. That's what. Okay, now look here. So there is one important thing to note. Suppose if I know an element of O3 group here, is it? And I want to figure out a corresponding element where? In SU2. What do you need to know? So you divide the generator by 2, is it? And put a corresponding Pauli spin matrix. Okay, so let me put it in a general fashion, then you will know. Okay? Okay. So in general, I will write like this thing. In general, suppose if your unitary transform, okay, this rotation is given by through an angle, let's say through some arbitrary unit vector. Clear? So let me define this Rn. Okay, so e raised power I, this j dot n theta. Okay, clear? Where j is the generator corresponding to a rotation along nth direction. You will be having only 3 generators. This is a rotation through an arbitrary angle. Clear? So I am not considering here jx, jy and jz. It is simply the rotation about an arbitrary angle. Clear? So n theta. So this is a unit vector in 3 dimensions. N. Okay. So this is equivalent actually to a unitary transformation. Let's say through this arbitrary angle is equal to e raised power I. Can anyone tell me? This sigma. Because in two-dimensional space, what are the generators now? These are Pauli spin matrices. Clear? So 2 by 2 matrices. For the time being, I don't know whether they are Pauli spin matrices or not. They are simply a 2 by 2 matrix. Let's call them as sigma. Okay? And you put the same unit vector n, let's say theta, but what you have to divide? 2. Clear? Now tell me what are the generators satisfying here? So these are the angular momentum generators, is it? So because they generate what? The rotation in your 3D space. Clear? Tisha, what these J is represented? They are simply, obviously they are the generators of the rotation. What they represent? They are simply angular momentum operators. Okay? So if let's say what kind of angular momentum operators they can be? Simply orbital angular momentum. Let's say for an electron, what kind of angular momentum operator? They will be simply orbital angular momentum operators, is it? Because they generate rotation where? In three-dimensional space. Clear? So you can think them, let's assume they are the orbital, although they can be general, they can be total angular momentum operators, or they can be in more general to angular momentum operators. Clear? It is not necessarily they can be of a specific type, but let's assume they are orbital angular momentum in nature. Clear? So, if I restrict my space to the real space, let me say they are actually angular momentum operators. Clear? Okay, so what is the algebra satisfied here? Ji, Jj. So this is the Lie algebra satisfied? Jk. Clear? Okay? This is the angular momentum commutation. This is the satisfied by what? So you take two, let's say Lx, Ly, it will generate the rotation by Lz operator. Clear? Okay, so now this is very important point. If you are having this set of generators, if you are having two groups, they are, let's say, isomorphic to each other. Let's think of two continuous groups, they are isomorphic to each other. Then their generators satisfy the same kind of Lie algebra. Same Lie algebra. It means, okay, let's think of the discrete groups. What it exactly means, this isomorphism. You know the group table. Group table means simply the multiplication of the elements of the group. Clear? So let me give you an example. Let's say you are having this Z2 group, 1 and minus 1. How you define the multiplication? Because it is the group under what? So 1 minus 1, 1 minus 1. So it will be 1 minus 1 and 1. Clear? So under group multiplication is here simply multiplication, simple multiplication, is it? Because this is a group under this simple multiplication. Clear? So these all elements should belong to the group. So when you do the group multiplication, the multiplication between the elements, they should generate the elements of the group. Clear? So, now let's assume there is another group which is isomorphic to this Z2. Clear? So what does that mean? You simply replace the elements of that group here. You simply replace the elements of this table by the elements of that very group. So that means you cannot distinguish between two, multiplication tables. This is a simple way to understand this isomorphism. Clear? Now similarly, if you are having two continuous groups, they are isomorphic to each other. Now if the generators of one group satisfy one Lie algebra, okay, satisfy some Lie algebra, then the generators of the other group satisfy the same algebra. So you just simply replace these by the generators of that group which is isomorphic. Clear? So now what it implies then? What is the generator here? It is sigma by 2. Clear? So that means you are having this sigma I by 2. I means x, y, z are 1, 2, 3. And sigma j by 2. What it has to be equal to? I epsilon I j k. Let's say sigma k by 2. Now what is that equal to? Sigma I, sigma j is equal to twice I epsilon I j k sigma. Clear? So you know that's actually equal to, let's say, sigma x, sigma y. What is that equal to? Twice I, sigma z, and so on. So समझ you got my point. So that means the algebra, let's say the angular momentum, let's assume these j's are the angular momentum operators. That means the algebra which is satisfied by these angular momentum operators j is also satisfied by what? So you will be having the same type of rules satisfied by these sigma operators. समझ? So that's why if you see in the quantum mechanics textbooks, what you see? So they introduce only what? Orbital angular momentum, is it? So and then assume spin to be of the same kind, spin angular momentum, is it? And do the same kind of algebra. Huh? The basic reason is, this is the foundational reason for that doing the same algebra of the spin operators based on the angular momentum, the usual orbital angular momentum operator. Huh? Can't be. 2 2s are 4. So that clear? Got it? Any question? समझ? So that is yes. So we have, therefore now we have seen this SU2 and O3 are isomorphic to each other. Okay, clear? Okay, so let's little bit evaluate this very operator. So this will be useful in many cases. Okay, so can you do it? So it's very simple. Now tell me what is sigma dot n square. Let's take this sigma dot n square. What is sigma dot n square? N is a unit vector along an arbitrary direction. What is the square of n? It is n. Clear? What is the square of sigma? 1. Because they are the Pauli spin matrices. So that means, so it will be simply an identity matrix. Clear? So now let's take sigma dot n even. So if you are having n, so that will be equal to identity if n is even, and it will be simply equal to sigma dot n if n is odd. Clear? So now let's write this thing, this sigma dot. So e raised of I sigma dot n theta by 2. Let's write it. So I can write it in this way. Can anybody tell me? So let's write. So it will be identity plus I sigma dot n by 2 theta, clear? Then minus sigma dot n square by 2 factorial theta by 2 square, clear? Then plus I sigma dot n cube. Is it plus or minus? So it will be plus I cube, that is minus I n. So it's minus I, so it is theta by 3 factorial theta by 2 cube plus 2. So now what this object is? This is identity. So what do you get? So identity minus theta square and so on, what you will get? You will get some identity times cosine of theta by 2. Then you are having plus I, sigma dot n will come out. Okay? So then you will be having sine of theta by 2. Clear? So we can write the element, or we can write this SU2 transformation in this form. Clear? So this is an identity matrix, cosine of theta plus I, this sigma dot n. Clear? Now you can put, let's say, n along z direction. So it will be sigma dot z. So that is simply sigma z. Clear? Only the z component will contribute, and so on. You can do anything. Okay? Got it?